Hello everyone, welcome to the next lecture on the Mobius transformation. Today I will explain you the concept of the pole and the critical points of the Mobius transformation. Myself Dr. Harish Garg, you can follow and subscribe my YouTube channel. Now what we have discussed so far, we have covered the concept of the Mobius transformation in our last lectures. You can find the lectures under the playlist complex analysis of my channel Dr. Harish Garg. You can see the Mobius transformations and many more lectures available in this playlist. You can follow it and subscribe my channel so that you can get the easy notification of all these lectures. What we have discussed so far, whenever you have a transformation AZ plus B divided by CZ plus D, where A, B, C, D are my complex constants such that AD minus BC is non-zero, then the equation number 1, the transformation equation number 1 is called as a linear fractional transformation. It is also known as the Mobius transformations or bilinear transformations. The term AD minus BC is known as determinant of the transformation, and when this constant value is come to be 1, we call as the normalized bilinear transformation. Now look at that. The first definition that we needed is the pole. What is the meaning of the pole? In a very simple meaning, the pole means your target is to find the value of the z for which t of z becomes infinity. Fine. For example, if I consider the Mobius transformation, let's say 2z minus 3 over 4z plus 7, can you find the value of the z so that t of z becomes infinity? Yes, of course you can find. The value of the z becomes minus 7 over 4. So therefore you can see minus 7 over 4 is the pole of the equation number 1. Similarly, for this case, can you think about the pole? So clearly say the pole will be minus d over c is the pole. But make sure this will happen only if AZ plus B is my non-zero at the point minus d over c. Is it okay? Now how you can prove that in a very simple manner? I can write the given equations. If c is equal to non-zero, I can write as a number is a over c. Fine. I can write the numerator part is phi of z and z plus d over c. Is it okay? Now to prove z is equal to minus d over c is a pole, what you want to prove? I need to prove only phi of d by c is my non-zero. Fine. So let's start with the phi of minus d over c. So that becomes a over c minus d over c plus b over a. Now you can take the LCM. It's a 1 over c square. It is bc minus AD. Now clearly say, because the given transformation is my Mobius transformation, therefore AD minus BC is my non-zero and C is my non-zero, this number is my non-zero. Therefore Z is equal to minus D over C is my simple pole. Hence T of is my infinity. Here one important point is noted here is there are the two kind of the transformations or the mapping. One is the C, second is the C infinity. C of infinity we call as the extended complex plane. This is called as the extended complex plane, or it is also known as Riemann sphere, or this is also known as closed complex plane. What is the difference between the C and the C infinity? There is a huge difference between them. The C infinity is a collection of all those elements of the C, including the point infinity. Fine. So if I define the mapping from C to C, then clearly say Z is equal to infinity is not the part of the C. However, if I define the infinity to C infinity, then we can say Z is infinity is the part of C infinity. Fine. That is a basic difference between them. Now whenever we can say C is my non-zero, then we can say T is a one-to-one mapping of the, now you can see this extended complex plane, that is C infinity. If I define the mapping is AZ plus B over CZ plus D, can you define the values? Whenever C is equal to 0, you can see if C is equal to 0, then your mapping is AZ plus B over D, and whenever Z is equal to infinity, the answer is infinity. Whenever C is my non-zero, then what is the value of the T of Z is infinity? Again, it is an infinity by infinity form. You can apply the L'Hopital rule. That value becomes A over C. Whenever Z is equal to minus D over C, if you substitute Z is equal to minus D over C, the answer is infinity. Whenever Z is not equal to minus D over C, Z is not infinity, the answer is remain the same, AZ plus B, CZ plus D. So what you conclude from that? That means T is the mapping, infinity is the domain part, so that is a C infinity. The codomain is also C infinity. Therefore, we can define the continuous map from the C infinity to C infinity. Always remember, student, if you define the map from the C to C, then clearly say this number is my not continuous. Why? Because infinity is not belongs to the C. Second concept. The second concept is we define the critical point. What is the critical point? Your target is to find the value of the Z such that the derivative of the transformation becomes 0 or infinity. Fine. As we can define the pole, remember I can quickly recall that. What is the pole? Your target is to find the value of the Z such that T of Z becomes infinity. That's a pole. While the critical point is all those Z's so that the derivative becomes a 0 or infinity. Fine. 0 or infinity. But we all know the Mobius transformation is a conformal mapping. All the Mobius transformation follows the conformal property. And what is the conformal property? Derivative is my non-zero. So once the derivative is my non-zero, therefore you can say there is no critical point in the finite complex plane. What is the meaning of the finite complex plane? That is a C. Whenever we are talking about the finite complex plane, fine, that means we are talking about the C. But if we are talking about the extended complex plane or closed complex plane, fine, then we are talking about the C infinity. So whenever we have the finite complex plane, there is no critical point. But if you're talking about the C infinity, then definitely there is a critical point. So for the case of the, like I can drive for you, whenever you have the Mobius transformation, T of Z is AZ plus B over CZ plus D such that AD minus BC is non-zero. So can you find the value of the derivative? So if you take the LCM, or if you take the U over V, AD plus, so it's a CZ plus D into A minus AZ plus B into C. So if you open the bracket, ACZ cancel, AD minus BC divided by CZ plus D. So clearly say this number is my non-zero. Why? Because the numerator is my non-zero. Also, this number is not infinity. Why? Because whenever Z is equal to 0, still this number is my. So therefore you can say T has no critical point. But can you say this, because we have seen this number is my non-zero, can you say this number becomes infinity? For what value of the Z so that this becomes infinity? So clearly say Z is equal to minus D over C. Fine. Whenever Z is equal to minus D over C, then T of Z becomes infinity. So then it is a critical point. But that critical point is occurring only in the extended complex plane, not in the finite complex plane. So we can say the AD minus BC is my non-zero. So there is a one-to-one mapping on this domain. So as I mentioned you, whenever Z is equal to minus D over C, then the value of the T dash Z is my infinity. And whenever the value of the Z is infinity, then T dash of Z is again 0. So what can you say? That means z is equal to infinity, and minus d over c are the critical points, but they are critical points in the extended complex plane, not in the finite complex plane. For example, if you consider, now you can see that function is not defined. So unless it is given, the function is always from the finite complex plane to the finite complex plane. फाइन, जब तक आपको ये कहा ना जाए कि डोमेन आपकी एक्सटेंडेड कॉम्प्लेक्स प्लेन है, तब तक आपका हमेशा फाइनाइट ही होगा. फर्स्टली चेक वेदर इज इट अ Mobius transformation. How you can check about the Mobius transformation? You can compare with the AZ plus B over CZ plus D. What is my A? A is 1, B is 1, C is 1, D is equal to minus 2. And when it will a Mobius transformation, if it hold, AD minus BC is non-zero. And clearly say this number is my minus 3, which is non-zero. Yes, this is my Mobius transformation. Once this is a Mobius transformation, we can target to find the pole and the critical region. How you can find the pole? I can put the denominator part as a 0, which implies Z is equal to 2 is the pole of the Mobius transformation. Second case is how you can find the critical point. As we have defined, the critical point is AD, or you can find the derivative of the Mobius transformation directly. Fine. So what is the AD minus BC? As I defined, AD minus BC is my minus 3. So we can define T dash is my, I can write for you here, T dash of Z is minus 3 over Z minus 2 whole square, and clearly say this number is my non-zero. Therefore, there is no critical point in the finite domain. Fine. But if somebody will ask you find the critical point in the extended complex plane, then what is the value of the Z? Then clearly say Z is equal to 2 is also the critical point, because the value at the T dash of 2 becomes my infinity. Look at the second case. Is it a Mobius transformations? A is equal to 2, B is equal to 3, C is equal to 4, D is equal to 5. What is the value of the AD minus BC? So 10 minus 12 minus 2, which is non-zero. Yes, this is the Mobius transformation. How you can find the pole? You can substitute the denominator part as a 0, which implies Z is equal to minus 5 over 4 is the required pole. Because you can also see that Z is equal to minus 5 by 4 is a pole, because the numerator value, which is my non-zero at Z is equal to minus 5 over 4. How you can find the critical point? I can find the derivative. So because it's a Mobius transformation, I can write directly the denominator square. Numerator is AD minus BC. And again you can see which number is my non-zero. Therefore, there is no critical point in the finite complex plane C. Look at the third case. Is it the Mobius transformation? A is equal to 1, B is equal to 0, C is equal to 1, D is equal to iota. Therefore, AD minus BC is iota, which is non-zero. Yes, it's a Mobius transformation. So can you find the pole? Z is equal to minus iota is the pole. Why? Because numerator part is my non-zero. What is the critical point? You can find the T dash of Z, the denominator whole square, and the numerator is AD minus BC. Clearly say this number is my non-zero in the finite complex plane. Fine. Now look at this another one. Is it a Mobius transformation? A will be coefficient of the Z, B is my constant, C will be 3, D will be 1. So what is my AD minus BC? So this is minus 1 minus 6, that is minus 7, which is my non-zero. So can you find the pole? Pole will be 3Z plus 1 is equal to 0. Z is equal to minus 1 over 3 is the simple pole. Again you can see the numerator part is my non-zero. Therefore Z is minus 1 over 3 is the pole. How you can find the critical point? we can find the value of the t dash of z. The denominator becomes 3z plus 1 whole square, and the numerator is AD minus BC. Again, you can see this number is my non-zero. Now, because we have seen that the Mobius transformation, any Mobius transformation has no critical point in the finite domain, or you can say in the finite complex plane. Fine. And we have seen the various example as well. Every time we have obtained the no critical point. Fine. But Mobius transformation has a no critical point in the extended complex plane, or initially you can say has no critical point in the finite complex plane. But if you have the extended complex plane, then it is possible that z is equal to infinity or some another point has a critical point. Then the reason behind is because it's a conformal, but the most important thing is the Mobius transformations are the only transformations. That is the most important word, are the only rational functions which has a no critical point. If you have some another rational functions like 1 over z square, 1 over z plus 1, z square plus 1, these are also the rational function. It may have a critical point as well. For example, I can provide you some rational functions with critical points. First of all, can you say the function t of z is a Mobius transformation? 1 over z square is a Mobius transformation. You can compare, can it be a Mobius transformation? No, because of this square. But Mobius transformation is always working as a linear. Clear? So this is not Mobius transformation. But yes, this function is my rational function. Fine. So can it be a critical point? Can have a critical points? Yes, of course you can. So how you can find? You can find the derivative. Derivative becomes minus 2 over z cube. So can you find the value of the z? Can you find the value of the z so that t dash of z becomes a 0 or infinity? So clearly say z is equal to infinity is my critical point. Z is equal to infinity is the critical point. Look at the second case. If you have the z square minus 1, again this number is my not Mobius transformations, but yes, this function is my rational function. Fine. So can you find the value of the t dash? So again you can start with the u over v. It is v square, then it is z square plus 1 into 2z, z square minus 1 into 2z. So if you open the bracket, it will be z square cancel, it's a 4z divided by z square plus 1 whole square. Fine. Now can it be 0? This is 0 if z is equal to 0. Therefore you can say z is equal to 0 is the critical point. Fine. Z is equal to 0 is the critical point. Second case is, can you find the value of the z so that t dash of z becomes infinity? Because the critical point becomes whenever t dash goes to the 0 or t dash goes to the infinity. That's the point is called as critical point. Now what can you say about the infinity? The easiest way is we can check about the limit. Z approaches infinity of the t dash of z. So what is the value of the t dash? So again it's an infinity by infinity form. I can apply the L'Hopital rule. So that becomes 2 into z square plus 1 into 2z, and clearly say this becomes my 0. Fine. So what can you say? That means z is equal to infinity is my critical point. This is the first method. You can easily check about that. Second method is I can choose w is equal to 1 over z. As the z approaches infinity, w becomes 0. Fine. Then I can find the value of the t of w. Fine. I can substitute the value of the z is 1 over w in the given equation. 1 minus w square, 1 plus w square. And what is the value of that t dash? Fine. If you take the derivative, you will get as minus 4w divided by 1 plus. Fine. Now because this is a function. So what is the value? Whenever w belongs to the 0, then this value goes to the 0. It implies w is equal to 0 is the critical point of t 1 over w. W is equal to 0 implies z approaches infinity is the critical point of t of z. Fine. Hence 0 and infinity both are my critical point of the given function. Look at the another one. Again, this is not the Mobius transformations. So if you find the derivative, so clearly say z is equal to 0 is my critical point. What can you say about the infinity? If again I can start with the t of, what is the value of t? It is 1 over w square. I can start with the t dash of 1 over w. This number is minus 2 over w cube. Whenever z approaches 0, this value infinity. What does it means? W is equal to 0 is not critical point of t 1 over w. This implies z is infinity is not critical point of t 1 over z. Hence 0 is the only critical point of the given function. Okay, the next important result is T defines the one-to-one mapping. T defines the one-to-one mappings of the extended complex plane. Extended means closed z plane to the closed w plane. Fine. That is the meaning of this. Now the Mobius transformation means az plus b such that ad minus bc is my non-zero. Now what is the meaning of the 1 1? 1 1 means you can start from the t of z1 which is t of z2 and your target is to prove z1 is equal to z2. This is your target. If you prove this result, that implies my transformation is 1. So let's start with the, let z1 and z2 are the two functions or the two elements from the domains minus d over c such that t of z1 is equal to t of z2. I can substitute t of z1 is a z1 plus b c z1 plus d which is equal to a z2 plus b over c z2 plus d. I can cross multiply them. It is ac z1 z2 plus ad z1 plus bc z2 plus bd which is equal to ac z1 z2 plus so on. Now you can cancel out ac z1 z2 cancel, bd and bd cancel. Fine. So now you can see I can take an z1 is a common, then it's a ad minus bc. On the right hand side I can take an z2 is here, ad minus bc. Now because 1 is the Mobius transformation, ad minus bc is my non-zero, therefore you can see these two numbers are cancelled, hence z1 is equal to z2. Therefore the transformation is my 1 1. So we can say the mapping is a 1 1 from the domain C d minus e, and if you define as a t inverse of w, fine, so that number becomes c of w plus b divided by c of z minus a, and clearly say c minus a over c is defined for the inverse. But how the a by c came into the picture? Look at that. Whenever you have a transformations, fine, can you solve this expression az plus b over cz plus d? If you solve them, cwz plus d into w minus az minus b is equal to 0. Can you find the value of the z? So z becomes minus dw plus b divided by cw minus a. So z becomes, can you find the value of the z is t inverse of w is my expression. Fine. And clearly say that domain is defined only c minus a over c. Therefore you can say that domain is defined c minus a over c. Fine. So this is the way you can think about the pole and the critical point of the Mobius transformation. We will see the next lecture very soon on the very important topics, matrix representation of the Mobius transformation. And the next lecture is very, very useful for the CSR net and the GATE examination. Till then, you can subscribe my YouTube channel. You can share this video with your friends. You can like and comment on the videos. Happy learning always. Thanks for the watching.